right? So the essence of it is quite simple, right? All this divide and conquer, greedy and all of those things, they are all good techniques, but we are trying to look for continuous improvement, and dynamic programming is one way of improving it. Most of the dynamic programming algorithms, the computing time, the time complexity that we talk about, there are the order of O of n squared or O of n cube. Okay? Order of n squared, order of n cube, and raised to 3, most of them. Significant improvement over divide and conquer. Okay? So that is the reason why we do dynamic programming now. The way it works is you are basically breaking down the problem into smaller sub-problems, okay, and solving the sub-problems. The neat thing about solving the sub-problems is once you solve a sub-problem, you save the answer in memory. So that way you don't have to keep solving the same sub-problem over and over and over again. For example, let's take the classic factorial. Okay? N factorial is what? N times n minus 1, n minus 2, and so on, right? The way it works is we use recursion, right? That is how we write a factorial thing, or even a Fibonacci sequence. So if you're writing that one, each of those sub-problems, like n minus 1 factorial, n minus 2 factorial, at every stage in the recursion they are being computed over and over again in a standard recursive call. It's a waste of time, right? You have already calculated once, you may as well save it in memory and access it and then move on, right? So that is what dynamic programming gives. You can solve it once and then save it and then reuse it. That is like a high level thing. Now there is no coming up with dynamic programming again. There is nothing like the word itself, as I told you, is a misnomer, right? There is nothing dynamic about it, because the moment you talk about dynamic, generally we tend to think like dynamic memory allocation, right, on the heap. We are not using it in that sense here. Let's look at what we have here. Sharing will end. I don't want to change it. So here is some quick thing about, from an exam viewpoint, you just need to review these things. I'm not going to go through each and every bullet. If I can even wrap up the review in 1 hour, I will do so. Okay. What is the difference, right? Both are optimization techniques. Okay. Now, when you do greedy, you know that you make a choice, you move on, you never go back, right? Whatever decision you make, like if you take the shortest path between source and destination, you have 3 branches, you take the lowest branch, you go to node B, and that's it, you never go back. Whereas in dynamic programming, what we try to do is we solve it bottom-up approach, meaning you're breaking a problem into smaller sub-problems, you're solving them, okay? When you're solving many of those sub-problems, then you come to the state where you say, okay, I'm going to choose these paths. Okay? Now, how do we do that selection of sub-problems? Which one is the ideal set for us? Use this principle of optimality. Okay? If you recall, principle of optimality. Okay. So what is the principle of optimality? You're looking at optimal solutions to the sub-problems, and when you recursively continue to choose the optimal ways of optimal solutions, optimal sub-problems, not optimal sub-problems for which optimal solutions exist, then overall solution would be optimal. Okay. Now, what is a cheat sheet example that we can remember to remember the principle of optimality? See, the trick is, right, all of a sudden you are asked this question, what is principle of optimality? Demonstrate your understanding with an example. You should have some example which is hardwired in your brain. Okay? So one example that I gave you, let me put it here, right? I don't think I copied that slide here, but let me create a slide here. Principle of optimality, right? Example illustration, right? Remember the coin example? The moment you see this, you should remember the coin example. What is the coin example that we had? It is so hardwired in my memory. If I say the 13 cents problem. Okay. And then when I talked about 13 cents problem, then I said, hey, you're trying to, what is the problem there? Coin example. You're combining different coins for a particular denomination, right? So in the case I want to put together, you have 1 cent coin. I can even tell you, like, you have 1 cent, 5 cents, 10 cents, 25 cents. You can replace cents with the paisa or whatever they call it. Yeah, paisa, right? India. So if I have a 13 cent problem to solve, dynamic programming says I'm going to create 2 sub-problems, right? Now what are the 2 sub-problems there? I can solve it for 6 cents and I can solve it for 7 cents. Okay? That is one approach. Now 6 plus 7 makes 13, right? So the sub-problems are determine how many coins for 6 cents, determine how many coins for 7 cents, add up and you get how many total number of coins. Okay? Now each coin, that basically means you should translate it to that many computations, right? The goal is to reduce the number of computations, remember that. Now, I can also come up with another combination called 11 cents and 2 cents. Correct? Okay. I won't go this slow for the rest of it. Here I'm just giving you a refresher here. If I do 6 cents and 7 cents, how many coins that will be? I will have a 5 cent coin plus 1 cent coin for the 6 cents. Then I will have another 5 cent coin, another 1 cent coin and another 1 cent coin. So that's total of how many? Let me make this corner. 1, 2, 3, 4, 5 coins, correct? 1, 2, 3, 4, 5. If I do the 11 plus 2 sub-problem, meaning I'm breaking down the bigger problem of solving 13 cents into 2 sub-problems called solve it for 11 cents and solve it for 2 cents. Then I can get 10 cents with using 10 and 1. And I can get 2 cents doing 1 and 1. So this is equal to 5 coins. 5 coins is equivalent to 5 computations. And this is equivalent to 4 coins. So which sub-problems are ideal for us? 11 and 2. So how can we determine which of the sub-problems are ideal? That in itself is a big exercise, right? Okay. So that is what we mean by principle of optimality. So going back here, I have the chat open. We do have the chat open, but I can't see the thing there. Okay. So basically you're splitting the input, right? And then you synthesize the larger solution from the small ones. Now divide and conquer, when we did that, all the splitting is happening in the middle, or depending on which problem it is, right? It could be slightly, it may not always be in the middle, okay? But in general, that is where it is. Dynamic programming, what it does is, it splits its input at every possible split point. Okay? Then you're trying all the split points and it determines which split point is optimal. So you're doing more work up front. Okay? To understand that, right? So it's more work up front, but once you finish that, the solutions are saved in memory, so that way you don't have to redo the same thing over and over again. That is how you increase the time complexity of dynamic programming. So in the case of 13 cents, the split points, I showed you 2 split points, 7 and 6 and 11 and 2. There could be other split points too, based on all the coin denominations. So your programming will do all those split points. That is what this slide is saying. So what is the definition here of optimality? It is, the problem is said to satisfy the principle of optimality if the sub-solutions of an optimal solution of the problem are themselves optimal solutions for the sub-problems. Meaning you cannot, by default, the sub-solutions have to be optimal. That is what it is telling you. So splitting the problem of 13 into 7 and 6 is not optimal. Okay? Whereas splitting them into 11 and 2 is optimal. Okay? That is, if you correlate this definition with the example, you will figure that out. Okay. Now we stressed a lot on this one when we did our full lecture on that, right? So if you have optimal solutions to all sub-problems, okay, it is never saying that if you combine all of them, then you will get an optimal solution. The relationship is not a two-way relationship, right? And then I gave you this example in the coins, right? Yes, for 7 cents, the optimal is 511. For 6 cents, 51. But together, it is not an optimal solution. So that is the trick to figure that out. Okay. I just put this slide here to tell you, when you are preparing for the exam, you say, okay, this is good. If somebody asks you, does the principle of optimality apply to the shortest path problem? Does it satisfy the principle of optimality? Yes or no? Who remembers whether it's a yes or a no answer? The answer is yes. For the shortest path problem, it does satisfy the principle of optimality. If you go back and review the slides, you will see that we did a small proof, right? If you have a path which says A, B, C, D, E, or A, B, C, okay? No, you need A, B, C, D, okay? If you take a subpath from there, you can prove by contradiction. You can do proof by contradiction, because if the subpath is not optimal, then from A to D, there must be some other path which gives you lesser path distance, right? So you use the proof by contradiction and say that yes, it does apply. Now for the longest path problem, does it satisfy the principle of optimality? Is it a yes or a no? I'll simply say it's a no. Okay? It's very easy to prove again that the principle of optimality is not satisfied. If you go back to our slide deck on the chapter, you will see in one of the slides I explained that. Okay. Now you know why I asked you to write questions, right? In the process of writing questions, as SVCW professor mentioned in one of the classes, That's the best way to learn stuff or review stuff. Writing questions. Okay. Let's continue to the next example here. Matrix multiplication. Right? This was another example that we considered. SV6. I know your name, but then please. I requested each faculty member to put their name in the chat. Jntuk, we already did that. Okay. So what is the matrix multiplication? What did we discuss in matrix multiplication? We said, hey, when I have a bunch of matrices, what is the right order? Remember, everything is about reducing the time it takes to finish it, right? Time computation, reducing the number of computations. So what is the order in which we should multiply the matrix? All these matrices. That is what we discussed in the in matrix multiplication problem, right? So, anyone remembers how we did that? I don't remember. So this is the matrix multiplication, right? For those of you who forgot matrix multiplication, row times column, you get the value, right? Row times column, that's where you get the value. So here is the full example here. Let me see here. So when I multiply them, the resulting matrix would have what? The columns P times R, right? So the total number of multiplications that will be there, we are multiplying P by Q and Q by R matrices, would be PQR multiplications. So you get AB equal to PQR, that many multiplications there. We are ignoring the additions because multiplication takes longer than addition, right? So remove the lower elements, take the higher degree elements. We talked about that in our video analysis, right? So in your exam, if you are given three matrices and they say, hey, the matrices have dimensions, and say which is better, A1, A2 first followed by A3, or A1 first A2, A3 you multiply, then you do the A1 times that, right? The way you compute the cost is, you have this formula PQR, right? You know what PQR are? Calculate the PQR for each of those combinations and then tell them which one is the right solution, okay? So that is, again, you're solving a subset, you're solving the sub-problems here, right? You have a bigger problem called three matrices or n matrices, and then you have to compute. The trick in dynamic programming is you have to compute for each of those things. So if you have A1, A2, A3, these are the combinations, but if you have n matrices, you'll have that many combinations to worry about. Now the thing that we talked about is optimal binary search trees. So we already saw enough of search trees, right? Thank you, Dharmaka. They were very nice. Great. So optimal binary search tree. Why do we call it optimal binary search tree? What was the context? The context in which we discussed this, we said we all know how to draw binary search trees, right? We have a root node and then you have two branches, right? And then left subtree, right subtree. Keep going down that list. At most two, right? Okay. If in your data somebody is, I'm getting some noise, can you mute yourself, please? Good morning, Pragati. So if a faculty member is there, please put your name in the chat, please. Okay, let me mute Pragati. I'm getting some static. Chaitanya, I'm muting you. I'm getting some static. CW I'm muting. Okay, great. So if we know a priori the frequency of the tree structure is a bunch of nodes, right? And you draw trees for all kinds of things, right? The meaning of the node can be, it is context sensitive. If you know the items which you access more frequently, if you put them close to the root, then you don't have to search all the way to the lowest depth of the tree. That is the principal idea behind optimal binary search trees. The more frequently accessed items you put close to the node. So we discussed the concept such as like some kind of a frequency table, right? And then the higher frequency ones, we put it close to the node. Now the advantage of doing those things, of course, in search time is enhanced. You get to it quickly. Okay. Now the other thing that you need to know is that you do not disturb the tree. Once it is done, you want it to be more stable. Okay. Now, since you want it to be more stable, what it means is you will not do too many insertions into that. Okay, because you already set up the keys. So I gave you an example, if you recall. Of when you have a key frequency, these are all the different keys that are available, and then you can see the frequency order in which they are done. And our goal is to build them optimal binary search trees to minimize the cost of accessing all the nodes. Okay, so when you are given a tree on the left and the table on the right, you compute the cost of accessing. How do you compute the cost? You're saying, hey, if you the order in which you are trying to do is C, A, B, F, D, G, E. So you are accessing it like that. So you compute the cost of C. To access C is at the root node. Root node is what it is. We are taking baseline as 1, right? 1 depth. We're starting at 1. In the case of computing this one. So A and F are level 2. First level is C. So you have first level, that means you access instantly, and the frequency is 1. So 1 times 1. Okay. Then you are saying after C you are accessing A. So where is A? A is at level 2. Okay. And then how many times A is accessed? Frequency is 4. So you get 2 times 4. Okay. Okay, one more we'll do and then we'll move on. B. B is at what? Level 3. Right? ఇది కరెక్ట్గా ఆర్డర్లో ఉండాలో తెలియదు పైన ఎఫ్ కాస్ట్, బట్ యూ కెన్ సీ హియర్ it is at level 3, and then B is accessed 2 times, so you should say 3 times 2, that is 3 times 2. Okay, like that you compute the cost. Okay, now contrast this with I don't know why I put that there. Okay, so I do not think that is optimal here, this particular example. Okay, you have the frequencies given in this one. So if you contrast that with we did an exercise here saying we can rearrange the tree to reduce the total cost. Okay, so you try to do this exercise again, not in the class today, but do it yourself. We did that in the class. To see how you can redraw that binary search tree to make it more optimal than what it is. Okay, and use the definition that we need to access all the nodes. Okay, so after you do that, you will see if after you do the exercise, you will see the solution to that. By rearranging the tree like this, your cost of accessing all the nodes will go down to 42. In the earlier case, it was 51. Okay, so hopefully this should give you some insights, like, hey, all these concepts do have a certain meaning, right? Why we do these things like that. The whole idea is we are trying to save time. when you're doing it over millions and millions of records, that adds up. So, what are we doing in dynamic programming? You are invoking bottom-up approach because you are solving sub-problems, right? And then whatever you solve, you save it in memory. So this is similar to the later examples where we talked about branch and bound algorithms. Some of them, we'll come back to that too shortly. So you create a search tree with one node, and the cost of that tree is the frequency of access to the root, right? We record those costs. Then you compute the cost of all the minimal trees, meaning you take K1 and K2 here, and then you do K2 and K3. You're doing pairs. Then you compute the cost by combining three nodes: K1, K2, K3, K2, K3, K4, like that, all the way till Kn. Okay. So once you know the cost of all of those things, then you know how to rearrange the tree to give you the optimal solution. Here is a big algorithm for that we did. We are not going to cover that now. So there is a formula. When you do all of those things, there is a formula to compute that search cost. The whole idea is when you rearrange like that, your search time is reduced, right? So we had this standard formula that we come up with. Then if you have that formula, it will be unfair for an examiner to ask you to compute these things without giving the formula. I assume that they would give the formula because I don't believe in it. But here is an example using that formula. If you have 5 keys and you have the search probabilities, which are listed here, right? Your goal is to calculate accessing all these nodes. What would be the total cost? Okay, that is what this total cost is. Total cost was 1 plus sum of these elements, right? That's what it showed you here. 1 plus depth of kth of I dot pi. So if you look at all, if you use that formula, it will come with 2.15. Here is another way of rearranging the tree. This is more normal binary search tree for the same thing, okay, where the estimated cost is coming to 2.10. So the purpose of the exercise is to basically figure out what is the best way to rearrange all these nodes in a tree, right? That is what we are doing here. Okay. So Pragati joined online. Pragati, whoever the faculty member of Pragati is, put the name please here. I'll type it here. Okay. So you can apply the dynamic programming technique to the knapsack problem, 0-1 knapsack problem. So if you were to do a brute force approach of figuring out what is the best way to do the 0-1 knapsack, 2 raised to n possible combinations of items, right? When you have 3 items, there are 8 combinations. When you have 4 items, there are 16 combinations and so on. Okay, so the running time obviously will be in the order of 2 raised to n. So if you can create the sub-problems in the right way and solve them, that huge exponential time algorithm would be reduced. Okay. So we did some example here. This was the example that we considered, saying how do you define a sub-problem, right? If you take only weights, okay, you can see here you have different items, 1, 2, 3, 4, 5. You have the weight and the value. value is called as benefit. Okay? There are two tables. There's this one where he considered what weight 2, 4, 5 and 3, which is 2, 4, 5 and 3, 2, 4, 5 and 3, the first four elements. Okay? If you consider those first four elements, your total weight is 14. I think the limit of the knapsack is 20 pounds. Okay? And then you get the maximum benefit of 20. Whether if you do it slightly differently as S5, where you took 2, 4, 5 and 9, that is 2, 4, 5 and 9, 2, 4, 5 and 9, you can see the total weight is 20, but the maximum benefit is 26. With the right subproblem is where you arrive at an optimal solution. So in this knapsack, what he did was, remember the subproblems, the solutions of subproblems should be part of the overall solution, right? So we could not arrive at that here when we did the S4 and S5 because there's one factor missing there, or a parameter. So by adding that additional parameter, you now compute both P, K, W. W is the weight, K is the item. So here is a formula that has been used to arrive at a sub-problem optimization. Okay, pretty standard algorithm there. I'm not going to go to the algorithm there, but it's there for you to convince yourself. Okay. But why it works well in the case of a 0-1 thing is, if you look at the order here for that algorithm, if you compute it, the running time of that is n star W. Okay. So W is the weight, right? Whereas when you do the brute force, it's 2 raised to n. So advantage of dynamic programming. It basically reduces your algorithmic complexity or time complexity, as we call it. Now I gave an example of, hey, if we have 4 elements and weights here, we covered this example. Weight and benefit has been given. Okay. If you run the algorithm, we did a extensive trace of this algorithm, if you remember, right? I think we initialized everything to 0. Then we started building the trace. I put a couple of trace examples here, how you trace it. Okay. So you can go back and see, I think we did like 17 or 18 traces. Give you the illustration there. Again, this is a very legitimate question. As long as in the exam they give you the algorithm, you should be able to trace it like that. Okay, I just put a few illustrations how that is traced. Okay, so that is the knapsack. Dynamic programming works well for knapsack, and you already know greedy does not work for knapsack. We did a couple of counter examples as to how or why greedy does not work for knapsack. Okay. In the case of traveling salesman problem, we said that you can do these are all, the moment you get into traveling salesman problem, you get into, most of these things are called NP hard problems, right? They are very hard to solve. So what you do is you do the best that you can to get to the most, as best an optimal solution as possible. Okay? To prove something is 100% optimal, it's hard to prove that, right? For an NP hard problem, that basically means you cannot solve NP hard problems. So you apply some heuristics, some shortcuts, right? So these are some shortcuts that you apply to come up with. So you can do a local search, come up with some valid tour, and make local moves to improve the tour. We did that where we said, hey, we come up with some candidate tour. We also said twice around the algorithm, if you recall. We visit these nodes twice. We store the values and then as neighbors start exchanging shortcut messages, then you continue to improve your candidate tour that you came up with. So eventually at some point of time, you will have as best a tour as possible based on the knowledge and wisdom that you gain out of the knowledge shared between the neighbors. Okay? Now we tour, right? So we say, okay, select the nearest unvisited node. And from there you select that one. It doesn't matter where you start. Start somewhere. The idea is to cover all the nodes once. Okay. The complexity is half log n for that. Greedy algorithm is something similar, right? So you have a partial tour, empty, and then you keep adding the edges. Okay. And then very similar to nearest neighbor, except here you're not necessarily using the nearest neighbor. You're doing it as opposed to vertices based, you're doing it edge based. Remember, since the graph has both edges and the algorithm, we are taking the edge based work here. Again, that algorithm also, the worst case complexity is half log n. Either one works. If I have to give a summary thing of DP, this is what we covered. Okay, it's useful, not useful all the time. Okay, because you need to figure out how to somehow come up with these sub problems recursively. If you can do that, then it'll give you great running times. You can see here one example is W times N for knapsack. In general, DP is of the order of algorithms. The moment you get to 2 raised to something, it goes into the exponential space. Okay, remember that. Okay, let me pause here. You're not getting the audio. Okay, let me put something in the chat here. Can you hear me? SVCW is not able to hear me. What about others? Is everyone having audio problem? They are not able to hear me, or just SVCW? Okay, perfect now. Okay. SVCW, it could be problem at your end. Okay, now you're getting it. Okay, great. Maybe I just fell asleep, maybe. That's why you didn't hear my voice. Time now is midnight here. Okay. Now, how did we solve the traveling salesman problem? When we talked about dynamic concept of the spanning trees, right? We said the only difference between doing the full circle and this one is removing one node or one edge, right? Because in traveling salesman problem, you have to start at the source and come back to the source. Whereas when we talk about spanning trees, as such, we never come back to the source because it won't be a tree, right? It will become a cycle if you come back to the source. However, you can use the ideas of minimum spanning tree to apply to the traveling salesman problem. Okay, so that is what we discussed here. And one principle that we use there is the concept of triangular inequality. When you are going from a node U to W, and in between you have a U, V and V to W, the distance from U to W is less than or equal to going from U to V and V to W. I mean, it is too obvious. To me, it's almost like an axiom, right? It will always be truth. It is like, what do you call that? Self-evident truths, right? That's what axioms are. They are self-evident truths. So to me, this is a self-evident truth. right? In the spanning tree, you are basically converting the problem of the TSP problem into a minimum spanning tree problem. Okay, and we know how to compute the minimum spanning tree. And how do we do that? We discussed last class. Remember the Kruskal's algorithm? We reviewed that, and Prim's algorithm. Okay, so whenever you are given a traveling salesman problem, remember that, hey, I can map it to an MST and apply either one of those algorithms. Okay. Next two slides are actually, next two decks are actually pretty straight because we just covered them recently, right? You will still remember it. So what is the essence of backtracking? So you're trying out various sequence or decisions until you find the one that works. So you keep moving forward. Initially you don't have all the data with you. So you keep moving forward. When you reach a dead end, right, you backtrack to the earlier node. Then you try another branch. Okay? And then you continue to go. If you reach the solution, great. If you don't reach the solution, you reach a dead end. Either you reach the solution or we considered these nice little graphs that we had here, if you recall. So you start, you keep going this way and you reach a dead end, so you come back. Once you come back from the question mark, you're going to the right side of it. If you reach a dead end, you backtrack. Then you backtrack one more time, then you go forward like that. Okay? The goal is to come to this success node ultimately. So that is what you're doing. You're tracking problem into a tree structure, and we navigate the tree. And then whenever you reach a dead end, you backtrack to the immediate node from which you came, and then explore the other subtree from there. Okay. The algorithm itself is very simple, right? So as you traverse the nodes, at every node, if the node is your goal node, then return success. Meaning you're looking for some particular value, it's there, you return success. Now you did not come to success and you reached all the way to the leaf node, okay, then you return failure. In between the true is where step 3 is, right? We are exploring the child C of the node n, right? And recursively apply. If the C is successful, return success. But if you go to all the leaves and everything is returning failure, your ultimate value that you return is failure. We did some algorithm that I put there for you to convince yourself. Okay. I have the algorithm there. I copy pasted that algorithm for you to look at it. Okay. So we use the backtracking to solve the 8 queens problem, if you recall, right? So, okay, you're getting the voice, perfect. Okay, great. So when we do the 8 queens problem, that's placing 8 queens on the board, right? If you do it by brute force, you can see the permutations of the numbers. You get 8 factorial, 40,320. Okay? It uses all of them and checks. Okay. When you do backtracking, okay, since you are constructing the search tree where you apply the backtracking algorithm rules, where you eliminate non-solution board positions at a early stage, because not all the positions are valid, right? The moment you place a queen on a board, you already know one row, one diagonal, and one column is gone. So So there is no reason for you to perform those permutations, right? To check whether that's a valid position or not. So you're eliminating some positions. So from 40,320, because of the backtracking algorithm, your state space has come down to 15,720 possible positions. Okay? And then we talked about the pruning techniques, right? When you reach a dead end, you no longer need to pursue any sub-tree beyond a dead end. So by applying that improvement, you can see from 15,000 you further reduce it to 5,500 possible queen placements. So as you apply these additional sophisticated techniques, you can see we are reducing the number of computations in essence. That is what we are doing here. Okay, that was the 8 queens that we discussed. So you're creating the state space tree. Trees are a great friend for data structures and algorithms. So each of the nodes in this tree basically signifies the solution partially. Okay, and then as you keep building the tree, those edges are basically telling you, hey, that's a promising path. So that's how you extend the partial solution along that path. And the way this is important, okay? This one, the next bullet point is important. You are always searching the state space tree using a depth first search. That is the big difference between backtracking versus branch and bound, right? In branch and bound, we are not limited to depth first. We actually recommend doing a breadth first search in branch and bound most of the time, right? So that's the big difference. And then lastly, in backtracking, you prune non-promising nodes because you are reaching dead end, right? So if they cannot lead you to a solution, there is no need to continue to explore them. So you prune them away from your state space tree. So that way you save space as well as time. Sorry. So we did some examples of how to draw a state space tree for 4 queens, right? If you go back and look at our backtracking algorithm, and then we said, hey, this is how you draw. This is again a legitimate question. You start off by placing the queen in row 1, 1, right? And then you can see you go depth first. Remember, that's where you see 1. Next you go to the second branch, you see where queen is placed, and so on. And then the algorithm shows you how to backtrack. Eventually you come to the right side. Okay, you arrive at the solution here. That is 8 queens. Give me a 2-minute break. I need to drink a cup of. Let me get some water. Let's take a 2-minute break. Let me put it in the chat here. To certain number k. Okay. So you have these numbers 1, 3, 7, 15, 8, 10, and we said, hey, select the subset that 8, 10 gives you 19, 1, 3, 7, 8 gives you 19. That is the sum of subsets problem. Okay. So what did we do here? So you have you can of course come up with subsets for all the numbers together, right? You have n numbers, 2 raised to n combinations and all that stuff. You can do that big exhaustive search, right? Instead of doing that, by applying backtracking, applying the principles of eliminating dead ends and pruning the subtrees, we can. So a general thing here that this slide shows is if you have 4 elements, and then when you have 4 elements, when you're drawing a tree, you will have 16, right? 2 raised to 4, correct? But 16 combinations basically, So you can see all the 16 nodes there, how it has been done. Okay. So you can see what the node represents and what the child represents. Okay. So the way we drew that is, we said the root node contains 4 children. 4, and from there, once you did W1, you have W2, W3, W4. You build the tree like that. Okay. Now, as you keep going down the depth of the tree, you're always keeping track of the added sum is satisfying the explicit constraint. Okay. Meaning, if the sum is less than or equal to, in this case, what, 19 or whatever we said, you continue to build the tree. If the moment it goes greater than, you no longer have to build the tree. Okay? Meaning the constraint is not met, you would not generate any more subtrees, and you backtrack to the previous node. Okay? So remember, it's all depth first. I'm going to show you an example which we did in our class, is how do you construct that, right? So you can see the thing there. So our state space is 3, 5, 6, and 7, right? And then we start with 3, and they say we have the branch with 3, without 3. That is how you create the branch, right? So with 3, then you add, what are you adding once you go to 3 state? You're saying with 5, without 5. Okay. Now when you're doing those things, as you build the tree here, the 16 nodes totally, right? 0 to 15 are 16 nodes. And then you can see when you do these things, you ultimately arrive at some answer here, right? And the way you arrived at answer is by using the backtracking, right? See, as you can see here, we did not, after we put 6 here, the moment it exceeded greater than whatever the value that you are looking at, in this case 15, you stop there, you backtrack. Okay. So you build 0, 3, 8, 14 first. Then you build without 6. Okay. Without 6, and then you add the next number there. Okay. Then you do without 7. Okay. Like that you build a tree. Okay. So again, this is the question, right? You are given that state space and you say the value of interest is 15 in this case. You build a state space tree that can be used by backtracking, using the backtracking algorithm. Okay. I think this is the last one that we considered in that particular chapter, is the Hamiltonian circuit. What is the Hamiltonian circuit? We said that, hey, it's basically a traversal of all the nodes of a tree exactly once. That's what a Hamiltonian cycle is, right? So we considered this problem here. I think we have a concrete problem here. To basically cover all the nodes, A, B, C, D, E, F. And how do you apply backtracking? The author applies some rules here, right? You break the ties. You start alphabetically here. Okay. We start from A. From A we go to B. From B we go to C. Right? From then to D, then to E, then to F. Okay. Now from F, how do I get back to A? We can't in this case, correct? Then you backtrack. You backtrack to E. That's how you apply for Hamiltonian circuit problems. You apply the backtracking. It works great. Okay. So then to D and so on, right? So what do you do when you do all of those things? Ultimately, you arrive at a solution of a Hamiltonian path like this. I would think that this is also a legitimate question. I mean, we are not asking you to memorize the algorithm. As I told you, we'll give you the algorithm or a picture. I think I don't even need to give you the algorithm. I can just give you the top left figure, A, B, C, D, E, F, the diagram here, and I can ask you to come up with this bigger picture here for a Hamiltonian circuit. Okay? Because ultimately you have to come back to A. Start from A, cover all the nodes, and come back to A. Okay? This backtracking with a slight enhancement related to putting a bound. Okay? Again, these are all optimization techniques, right? That's what we are doing. So let me check. Coming up with the bounding function is not easy, as I told you. Okay, it's an approximation. Okay, so we make a best guess. Okay, and we think it is promising. Okay, as long as you can hear me, then let's put up with it. We are almost done. Okay, the noise is coming. Let me see if I have to mute anyone. Maybe it's coming because, give me a second, let me see if I have to mute anyone here. I should not mute myself. Some static somewhere, I don't know. All of you are muted actually. It's not my headset. I hope you are still able to hear me even though there is a little. For example, I think we gave some. I think we said that in a branch and bound type of traversal, we can do BFS breadth first or depth first. Okay, some theory here. Okay, and we use the bound. The reason why we use the bound is using the bound we can prune the tree, right? The whole idea is wherever you're drawing trees, whether it's backtracking or it's branch and bound, the name of the game is to prune the trees. That way you don't have to go through dead end. Yes. So we did the example of a traveling salesman, if I'm not mistaken, right? This was the example that we did, where we calculated the distance from like all pairs neighbors, right? That's what we did from A, what is the shortest distance to all the other nodes and so on. Okay. And then we said, okay, we can obtain some initial tour. What is the tour? The tour is basically you have to start at A and come back to A again. That is the tour, right? In traveling salesman. So we select some tour, and the way we select some tour is that there is something called like a greedy method. Greedy method always chooses, in this case, the shortest, right? So you start with some candidate tour here, that is the A, E, C, G, F, D, B, H, A, and you know the tour length for that. Okay, so once you do that, you kind of have a bound there. Okay, now once you have a bound, then you continue along the path of the promising tour. Remember, you go to A to E and so on. Okay, if you find another bound which is lower than what you have selected for the candidate tour, and here is an example that we discussed, how we did that, right? So you start with A. For each of these things, you said, okay, compute the minimum cost for every other node. There's a table that I gave you and all that. We came up with this minimum values. We know the candidate know the candidate tour is 28 in the previous slide. So anything greater than 28, you prune them out. Okay. So if you look at the 28 here, C, F, and H. Greater than that. So your object of interest would then become B, D, and E. Okay. Now once you know the promising nodes of B, D, and E, you select one of them. Okay. In a best first order. See, that is the other thing. In a best first order, because A, D, and D, the value there is 25. You select that one. Then you expand all the neighbors. Remember, from E, where are all the neighbors that you can go to? Non-visited node, B, C, D, E, F, G, H. Then you apply the same algorithm again. I did not take the full snapshot of it. Continue like that in the loop till you reach the destination. Okay. We even did this example, we gave you this exercise here for you to do that. We are not doing it here, but I put it here again because in the process of trying to prepare for the exam, you should go back and revisit this group exercise. You did it in groups, and if you do it one more time in groups like that, then you are all set for the exam. Okay. Here is the solution for that. Solution is put there too. Okay, so how do we solve the branch and bound? Somebody asked me this question. I said it really depends, right? But here is a little bit more depth on that. Obviously, if you do brute force, if there are n elements, there are 2 raised to n. We already know that, right? By applying a backtracking technique, you are basically getting a combination of n 2 raised to n over 2. Okay. You still see some, it's still a high number, right? Whereas I think if you do the knapsack problem using the dynamic programming approach, what did we say we will get? The dynamic programming approach gives you a better solution than using this approach of branch and bound and backtracking. Okay, and you can see the values do add up, right? 2 raised to 50 for and 50 elements would take 35 years, right? By saying, okay, half of the elements I use one technique and the other half I use another technique and do that, you can solve the problem in about 30 minutes. Okay. So what this example shows you is, it's not like you apply only one technique. Okay. You apply a combination of. Then we consider the least cost solution. So where we are basically, we introduce the concept of what do you call them? The nodes. I forget the names. I'm blanking out now. What were you calling it? The node that needs to be live node and E node. Remember the concept of E node and live nodes. We use the concept of those things to solve the least cost solution problem in branch and bound. And the example that we consider the puzzle, right? So you have an initial state here and you want to reach the styles plus the moves that we have done, right? So by going to that, and then we simplified it saying that moving one tile in any direction would cost 1 step. Okay. Then we went through this example of how to solve the problem here. there was a typo here, right? This 1 plus 4 is actually 1 plus 3 equal to 5. Okay, so we take we take each of the branches. How did we come up with these things? We said that, hey, in this empty space 4 can move there. Okay, if 4 moves there, okay, how many tiles are misplaced? 4 is misplaced, 6 is misplaced. 4 should be equal to 3, that's 4. If you see this one here, we moved 6 into this tile here. When you move 6 here, the misplaced tiles are, 6 is already in its right place. The misplaced tiles are really 4 and 5. So that is 2, the value 2 here. And 1 is the cost of moving. So that is 3. So you continue to do this one. Like that, I just took one snapshot to tell you, hey, this is what you need to review when you do the final exam. Go back and see the rest of the steps for that. Okay, and then cost. Okay, so execution time, branch and bound, is pretty significant. It takes less time than backtracking. Okay. One uses a priority queue and the other one uses stack. Okay. Now you can see here, backtracking may never find a solution if the tree depth is infinite. So in reality, all these different types of techniques that exist, we use it in different combinations. Okay, it's for the same problem we can use a multitude of these. So I am concluding my lecture with this quote today, and then I'll do a couple of other things after that. A very famous quote, I don't know how many of you have heard this, right? A journey of 1,000 miles begins with a single step. Lao was a contemporary of Confucius, the Chinese philosopher. Okay? What does it mean, right? To me, what it means is all these things that you're learning is really a journey, right, for your professional career. And to me, data structures is one of the foundational classes. So you have taken one more step. Programming skills in second year. Third step is, of course, the data structures and all that you're learning. Okay. So it takes a lot of effort, single step at a time. That's what this quote is all about. Okay, enough of talking. Didn't do any exercises today because it's kind of